Hi guys, welcome to your channel that brings convenience to your doorstep. Today I've come in with electrical engineering technology, also known as circuit theory. This is due to demand for this course, and I hope you are going to enjoy it. And more are still to come. Guys, just subscribe to your favorite channel that affords you the opportunity at your own time, pace, and a place to study. Guys, let us enjoy electrical engineering technology. You have heard the terms voltage, potential difference, EMF, resistance, resistivity, to name but just a few. I'm here to give you what you have been looking for. Hi guys, welcome to our first topic in electrical engineering technology, also known as circuit theory. Our first topic is fundamentals of electricity, and we'll be looking at the information that we need for us to understand electrical engineering. We'll be looking at electromotive force, potential difference, ammeter, voltmeter, resistance, resistivity, volt, farad, SI units, engineering notation, scientific notation, to name but just a few. Your presenter is Motion, and I hope you are going to enjoy. This is a new course apart from Electronics 1. Objectives. Guys, by the end of this presentation, make sure you are able to, this is very simple, you are able to state the basic and the basic quantities as well as electrical quantities. Normally we are most interested in electrical quantities because they are the ones we'll be talking about in this course of electrical engineering technology or circuit theory. We also must know their symbols and also there are units. The units of the quantities, the units of the symbols, and also their units, and also the symbols of the units. That's objective number one, and I know you'll be able to do that because we are taking over from what you did in your high school. Then write numbers, guys, mathematics in scientific as well as engineering notation. 2 times 4 to the power 2 times 4 times 10 to the power 3. That's scientific. Then demonstrate understanding of atomic structure by drawing when you are given atomic number or the number of electrons. Then you must also be able to define the following quantities in electricity. That's electromotive force, in short EMF, potential difference, in short PD, charge, resistance, resistivity, conductance, temperature, coefficient of resistance, as well as their units. You must also be able to demonstrate this important fact that the EMF, electromotive force of a source, is equal to the open circuit voltage when no load is connected. But when a load is connected to a source voltage, then the terminal voltage becomes less than the source voltage or the EMF because of the drop across the internal resistor. Guys, nothing tough. We'll be running through. This is basic material on electricity. Guys, let's enjoy. The introduction to the fundamentals of electricity. I think you guys would agree with me that not a day can pass without you interacting with electrical gadgets like computers, smartphones, the heating effects in our homes, or even at work, the lighting system in our homes, even at work, you name it, are all applications of electricity. Electricity is a form of energy that is clean, and we have other forms of energy like kinetic and light energy being converted to electricity, showing that it is very important in our everyday lives. It has been accepted that electrical engineering involves the generation, transmission, distribution, and utilization of electrical energy or electricity. To have a deeper understanding of electricity or electrical engineering, it is of paramount importance that we first look at the basics. So this presentation is going to look at fundamentals of electricity, which generally involves the basics of electricity. This involves discussing things like the structure of an atom, characteristics of an atom, the SI units, the basic quantities as well as the electrical quantities, schematic symbols that that are involved in electrical engineering: the volt, the charge, the EMF, potential difference, the metrics, prefixes like 10 to the power 3, 10 to the power 6, 10 to the power minus 12, like that, electrical engineering notation. These things must be known before we go deeper into the study of electrical engineering. And we are going to do that, and I know we'll be successful in that endeavor. Guys, let us enjoy. We are now looking at basic quantities, the symbol for the quantity, the SI unit, and the unit symbol. Length, the symbol is L, and the unit is meter, and the unit symbol is capital letter M. Then mass, the unit symbol is kg, the unit for mass is m. Time, the symbol is small letter t, time is measured in seconds, and this is the symbol for second, small letter s. Electric current, the symbol, please take note, it is capital letter I, the unit is amperes, and the unit symbol is capital letter A. Temperature, please take note, the SI unit is Kelvin, not degrees Celsius, and the symbol for temperature is capital letter T. It is measured in Kelvins, capital letter K. That's the symbol for Kelvin. Then we have got the luminous intensity and the amount of substance. These are not very important in electrical engineering per se. Since we are studying electrical engineering, it is important to have a look at electrical quantities, their symbols, the SI unit, and also the SI unit symbol. Guys, these are very, very important, and you will meet them so often in your course. The symbol, this is voltage, capital letter V is the symbol, and it is measured in volts. The symbol is V. Resistance, the symbol for resistance is capital letter R. It is measured in ohms, and this is the Greek symbol omega. A charge, the unit for charge is a capital letter Q. It is measured in coulomb, and the symbol for coulomb is capital letter C. Power, the symbol for power is capital letter P. It is measured in watts, and the unit is W. Then energy, the unit for energy is capital letter W. It is measured in joules, and the symbol is capital letter J. Then frequency, the symbol is small letter f. It is measured in hertz, and the symbol is Hz. Please take note, H is a capital letter. Then capacitance, the symbol for capacitance is C. It is measured in farads, capital letter F. Then the unit symbol is capital letter F. Then inductance, symbol is capital letter L. It is measured in henries, and the symbol for henries is capital letter H. Then conductance is with which a material can allow electricity to pass through. Its symbol is capital letter G. It is measured in Siemens, and the symbol is capital letter S. Please take note that conductance used to be measured in moles, MHO, which is rather ohm spelled backwards, and the symbol that was used then is this omega but inverted. Then resistivity, the symbol for resistivity is rho, and it is measured in ohmmeter, and this is the symbol. Then impedance, which you find in AC circuits, the symbol for impedance is capital letter Z. It is measured in ohms, just like resistance, and their units are also the same. It's omega. Why? It is because both refer to the opposition to the flow of current. Hence, you see that their units are the same, and also their symbols are the same. So, guys, make sure you master these quantities and their units. Guys, this slide is very, very important. The metrics, the metric prefix table, it is very, very important, because when we do our calculations, you will find that you will be required to know these powers and the name. So we'll start with the highest until we get to the lowest or to the least. Tera, for example, terabytes. The symbol for tera is capital letter T, and its value, or the power rather, or the exponential is 10 to the power 12, and this is equal to this value. Then giga, it's capital letter G, is 10 to the power 9, and it's equal to this value. Then mega, it's capital letter M, 10 to the power 6, and it is equal to this value, 1 million. Kilo, please take note, kilo is small letter k, and it is equal, in power form, it is equal to 10 to the power 3, and it is equal to this value. Centi, I think you are aware of centimeters. The symbol is capital letter C. It is equal to 10 to the power minus 2, and this is equal to 0.01. If you punch your calculator, you get this value. Millimeter, for example. Milliamps, the symbol is small letter m, and to the power of 10 is 10 to the power minus 3, and its value is equal to 0.001. Micro, this is the symbol for micro, and this is a Greek letter. It is in exponential form is 10 to the power minus 6, and this is equal to 0.00001. Then nano, that's small letter m, 10 to the power minus 9, and it's equal to this value. Then pico, small letter p, 10 to the power 12, and it is equal to this value. Guys, you must know this. This must be at your fingertips, or else you will not make it in electrical engineering or in circuit theory. These are the fundamentals which I thought we could study first before we go to the nitty-gritties of electrical engineering. Scientific notation is also a basic fundamental concept that must be known by students pursuing electrical engineering, and it is a special way of expressing very large and very small numbers. For example, 300 million meters per second in scientific notation is 3 times 10 to the power 8 meters per second, and this is the speed of light in a vacuum. Then this very big number in scientific notation is 1.6 times 10 to the power minus 19 coulomb, and this is the charge of one electron. So what basically is scientific notation? It is a product of a number between 1 and 10 and a power of 10. This is a number, n, capital letter N is a number between 1 and 10, and we have n times 10 to the power plus or minus n, and that is a power of 10. Then for practice sake, I've put some numbers in scientific notation and those that are not in scientific notation and commented thereafter. 7.6, this is between 1 and 10, so it's correct, and we have 10 to the power 3. If we compare it, 76 times 10 to the power 2, this is not in scientific notation. Why? Because 76 is greater than 10, and 76 is not between 1 and 10. But their values, or the numbers, are the same in value, they are equal. That is to say, 7.6 times 10 to the power 3 is the same as 76 times 10 to the power 2, but one is in scientific notation, the other is not. 8.2 times 10 to the power 13 is the same as 0.82 times 10 to the power 14, but that one is not in scientific notation because 0.82 is less than 1. 0.82 is not between 1 and 10. Then the last one, 5.37 times 10 to the power 7, that is the same as 53.7 times 10 to the power 6. Their values, or the numbers, are equal, but the second one, 53.7, is not in scientific notation. Why? Because 53 is greater than 10, and so 53 is not between 1 and 10. So guys, this is your high school mathematics. Practice it and make sure you are able to change from ordinary to scientific, or from scientific to ordinary. Then engineering notation. Engineering notation is almost the same as scientific notation, but the only difference is small letter n is a multiple of 3. So n can be 3, can be 6, it can be 9, it can be -3, -6, -9, etc. For example, these two numbers, this one is in scientific notation. Why? Because the power, we have got 10 to the power 3. This one also in engineering notation, it is 10 to the power -9. So n is a multiple of 3. But these two numbers are not in engineering notation. Why? Because the powers are not multiples of 3, and also these numbers are not between 76 and 53.7 are not between 1 and 10. So guys, engineering notation is important in electrical engineering because you realize that here and there we'll be referring to those to the metric table, whereby we had 10 to the power 9, 10 to the power 12, 10 to the power 6, n must be a multiple of 3. Guys, that slide is for you. I've got some problems which I want you to practice. If you find any challenges, you can get in touch with me. We've got this value, which is 2,340,000. In scientific notation, it is 2.34 times 10 to the power. I want you to put the value of n there. Then that's 0.000000234. It's 2.34. This value must be between 1 and 10, which means 1 to 9. Anything above 10 is not accepted, and anything less than 1 is not accepted. So I want the value of 9 there. Then these are very, very simple. Even if you punch them on your calculators, you get the actual value. So can you state this can you convert this to ordinary form, which we also call the standard form? If you face any challenges, guys, don't hesitate to get in touch with me. We want to discuss why is it important to learn electrical engineering. The first point is electrical engineering is the driving force and the supporting pillar for modern industry and civilization. Imagine a life without a computer, a life without a cell phone, a life without internet, because all these gadgets work on electricity. Then in our everyday life, it would be unthinkable without electricity or the use of these electronic gadgets. Then the other reason why it is important to study electricity or electric circuits is any complex electrical or electronic device is founded from basic theory of electric circuits. So it is important that when you are doing electronics, when you are doing electrical engineering, you study even the fundamentals or the electric circuits. Then the next point is only when you've grasped and understood the basic concepts and the principles of electric circuits can you do further study of electrical, electronic, and even computer engineering. So without the fundamentals, you cannot pursue the disciplines in more detail or in greater depth. Then last but not least, electrical, electronic, and computer engineering has made, and this you agree with me, and continue to make incredible contributions to our life. Computers, cell phones, internet, this is because of electricity. So it is important to study electric circuits, hence this presentation from me. This topic was covered in more detail in your Electronics 1 course, but however, there is no harm in repeating it. We are now going to look at electron theory. From your high school, you know what an element is. An element is a substance which cannot be decomposed into other smaller substances, and its smallest particle is called an atom. An atom is made up of electrons, protons, and neutrons. Guys, we did this in the first or second presentation. And we know the number of electrons is equal to the number of protons. And we also know that an electron is negatively charged and a proton is positively charged. Neutrons and protons are found in the nucleus of an atom. Electrons reside in orbital shells around the nucleus of an atom. That is it. Let's proceed to the next slide and look at the structure of an atom. The structure of an atom, we've got two structures, one for carbon and another one for copper. And as you can see, the K shell, which is the first shell from the nucleus, contains 2. Then the valence shell for carbon contains 4. Elements with or atoms with 4 electrons are called semiconductors. Then copper is a very good conductor. Just look at the number of electrons in its valence shell. The less the number of electrons, the better the conductivity. It has got 1. The inner shell has got 2. The second shell, which is the L shell, has got 8. The M shell has got 18. And this comes from 2n squared. 2n squared does not apply to the valence shell. So this is an illustration of the structure of an atom. Please take note that protons are found in the nucleus, hence the plus 6 and also the plus 29. Electrons reside in shells around the nucleus of an atom. And when an electron can lose or gain gain electrons in order to attain stability. So if copper, for example, loses 1 valence electron, it will have a charge of plus because we have more protons than electrons. An atom is said to be electrically neutral because the number of positive charges, which are protons, is equal to the number of negative charges, which are electrons. Excess electrons result in a negative charge. Deficiency of electron results in a positive charge. The loss or gaining of electrons by an atom is called ionization, and a charged atom is called an ion. Guys, you must be able to define those important terms. The charge of an atom that is gained and lost electrons must be taken note of, and this is deduced from the number of electrons when compared to the number of protons. The quantity that we are going to look at first, which is an electrical quantity, is called electric charge. What is electric charge or charge in electricity? It is the difference or the addition of excess electrons in an atom. That element, when it has got a deficiency or excess electrons, is said to be charged, which means it can have a positive or negative charge. Then please take note that the symbol for charge, as we saw in one of our previous slides, is capital letter Q. So the charge possessed by an electron, please take note that it is equal to 1.602 times 10 to the power 19 coulombs, and that is very, very small. Hence, to find the charge of electricity, or we use a coulomb, and a coulomb is larger than an electron. And we are saying 1 coulomb is the charge that is possessed by 6.24 times 10 to the power 18 electrons. So what have I just said? I've said 1.602 times 10 to the power minus 19 coulomb is the charge of 1 electron, but that isn't enough a measurable quantity. So in electricity, we use 6.24 times 10 to the power 18 electrons to represent the charge or the deficiency or the addition of excess electrons on an atom. When we add electrons or remove electrons from an atom, we change the charge, as you will see in the coming slide. The next quantity is electric current. You must be able to define a current. What is current? Current simply means the flow of charge. And in electricity, or in electrical engineering, we've got two types of currents, and please, you must take note of the two. We've got conventional flow of current, and this one came earlier than the electron current. Electron current is due to the movement of electrons. Conventional flow of current is due to the movement of protons. Scientists, when they started to work on the structure of atoms, they thought it was protons that moved. Hence, the issue of conventional flow of current assumed to be from positive to negative. Then later, it was discovered that there is an electron, and it is the one that moves. Then that's when we now have electron flow of current. And please take note, it is current that flows. EMF or voltage does not flow, rather it pushes the current and cause it to flow. So I'm saying later scientists discovered that electric current is actually a flow of negative charges, and that is electrons from the negative terminal of a battery through the load to its positive terminal. So take note of the two currents and their direction of flow. Must be able to define current. More on direction of current flow. As I said, conventional current flow is defined as a flow of positive charges, and positive charges are electrons from the positive terminal of a power supply or battery through the load to its negative terminal. And we'll be using that to analyze our DC circuits. Then electron flow version. This is the flow of negative charges, and that is electrons from the negative terminal of the power supply through the load and to its positive terminal. Guys, let me also point it out that it makes no difference insofar as circuit analysis is concerned, or the measuring of current voltage across the load is concerned, or even the analysis, design, calculation, measurement, and applications of electric circuits, as long as we are using one method consistently. And like I said, we'll be using conventional current flow version. An illustration of conventional current direction, which is Fig A, 1.2a, as well as electron flow direction. And as you can see, this is our positive supply and our load is a bulb. So the movement of positive charges, that is electrons, according to some scientists, from positive terminal through our load, which is the bulb, and to the negative terminal of the applied voltage. E stands for electromotive force. And please take note of this direction. For the electron flow direction is from the negative terminal of the battery through the load and to the positive terminal of the applied voltage. That is what we mean by the two types of currents, the conventional current flow as well as the electron current flow. And we'll be using this. Please take note. The relationship between charge and electric current, and we said Q is the symbol for charge and capital letter I is the symbol for electric current. So this is the relationship. Current is equal to charge divided by time. In simple form, I is equal to Q over T, where Q is charge, T is time in seconds. So a coulomb is a basic unit of the quantity of electric charge, and it represents 6.24, as we saw, by times 10 to the power 18. And we got this from the reciprocal of the charge of one electron. The symbol for coulomb is capital letter C. Guys, given charge in coulombs and time, you must be able to calculate current. And current is measured in amperes. Charge is measured in coulomb, and time is measured in seconds. Please take note that the symbol for time is not capital letter T. Capital letter T is for period. The symbol for for time is small letter t. We now want to define ampere, which is 1 amp. This is the total number of electrons having a charge of 1 coulomb that passes through a given cross-sectional area in 1 second. This is the definition for ampere. Total number of electrons having a charge of 1 coulomb that passes a given cross-sectional area in 1 second. It is defined like this. Guys, in electrical engineering technology, you can define using equations that is allowed. So ampere is equal to 1 coulomb divided by 1 second. So this is the relationship between charge, which is Q, and electric current, which is capital letter I. Ampere as the unit of current. 1 ampere is the rate of flow of electric current when 1 coulomb of electric charge passes a certain point in 1 second. That's the definition for ampere, and guys, or for 1 ampere, and guys, you must be able to define it. And as I said, the symbol for electric current is capital letter I, and the symbol for ampere is capital letter A. Then I have got a question. What is the current in an electric circuit when 75 coulombs of electric charge passes a certain point in the circuit in halfway time? So we are being asked to find electric current, which is capital letter I. So I is equals to Q over T, we saw from the relationship. Then that's 75 divided by 30. So this gives us 2.5 coulomb per second. 2.5 coulomb per second means 2.5 amps. Guys, given the 3 parameters, or given any 2, you must be able to find the other. This is mathematics. How to measure electric current, and also how to measure voltage or potential or difference. From your high school, an ammeter is an instrument that is used to measure current, and its symbol is capital letter A. As you can see, this is an ammeter, and also this is an ammeter. An ammeter has got very low resistance to the flow of current, hence it can be connected in series without introducing external resistance apart from the resistance of the load. Then V1, V2, and V3 are voltmeters. A voltmeter is used to measure voltage, and because it has got a high resistance, it is connected across a load or across a resistor. So that this means that V1 is not going to divert a current away from R1. The same applies to V2 as well as V3. Why? Because they've got a very high resistance to the flow of current. If we connect it in series, it means that no current will flow in that particular circuit, hence it will affect the measurements will be carrying out. Why? Because it has got a very high resistance to the flow of current. So this is the way how you measure voltage and current. This is measuring the voltage of the source, and this is measured the potential difference across R1, potential difference across R2, as well as potential difference across R3. This one is measuring the electromotive force. Don't worry, it's going to be clearer very soon what those two terms mean. Electromotive force, EMF. What is EMF? EMF is the force that drives a current in an electric circuit. And guys, take note of the first statement. Random motion of electrons within a material doesn't constitute electric current, just as the formation of the depletion layer due to movement of holes and electrons across the junction does not constitute electric current. It is drift current that constitutes electric current. For electrons to move in a given direction, we must apply electromotive force or voltage. So we are saying the electromotive force, just like the pressure that drives water to our homes or houses. It is the force in an electric circuit. It's a symbol, take note, it is capital letter E, and the unit is volt, capital letter V. And Sources, good sources of EMFs, we've got cells, and when we connect cells in series, it becomes a battery, and generators are also sources of EMF. EMF causes electrons to move around, or it causes current to flow through a circuit. So we say it is an electron moving force. It is the pressure or the force that is supplied by the voltage source, and it is the one that results in a current flow in a complete circuit. And please take note that the higher the EMF, the higher the current flow. And EMF is also known as voltage, just like potential difference. It is also known as voltage. We've got another 2 or more slides expounding on electromotive force. Potential difference, in short, PD. PD is a result of current flow through a load or through a resistor, and the potential difference is measured across a load and also across a resistor. A resistor is used as a load. Potential difference results from a current flowing through a resistor. It is only when a current flows through a resistor or load when a potential difference develops. Another word for potential is voltage. The unit of potential difference is volts, and it is the difference in voltage levels before the load and after the load. Please take note that for water to flow, there must be a slope, there must be a gradient. Otherwise, points on the same level cannot result in water flowing. You know that rivers flow because there is a gradient down the river. PD and EMF are measured in volts, but they are not the same. Essentially, EMF is a force that causes electrons to flow. Potential difference is the result of current flowing. So EMF is the cause, PD is the effect. What then? We now want to define volt. Volt is defined as, if the voltage between 2 points is 1 volt, it means that it requires 1 joule of energy to move 1 coulomb of charge from one point to the other. You see another clearer definition than that in the next slide, and you can choose which one to use. Volt is, or voltage, mathematically is stated as work divided by charge, where capital W represents work and it is measured in joules. Then Q is charge and it is measured in a coulomb. More on potential difference. Please take note, if you are asked to measure the voltage across or the voltage drop across a resistor, you are being asked to measure the potential difference. So potential difference is also known as a voltage, and it is produced by the EMF of the voltage source. It is the amount of energy or work that would be required to move electrons from one point to the other or between 2 points. And an important point to be taken note of, current only flows if there is a potential difference between the two. Why does water flow from one point to another? It is because there is a gradient, or the 2 points are not on the same point. There's a slope. So volt again is the amount of force necessary to cause 1 coulomb to produce 1 joule of work. Voltage, please take note that it cannot flow. It is current that flows. EMF and potential difference, and there are many names in electric circuits that mean the same. One is source voltage. Source voltage refers to the EMF. Applied voltage refers to the EMF. Load voltage is potential difference. Voltage drop is potential difference. Voltage rise is EMF. Normally we find voltage rise especially when we are applying Kirchhoff's voltage law. You will see the differences. EMF can be called source voltage or applied voltage, since it is supplied by a voltage source and applied to the load in a circuit. Load voltage is the voltage across the two terminals, and as we saw, this is PD. Voltage drop is PD. Voltage rise is across a component, normally a voltage source, and this is normally refers to an EMF source. I hope, guys, you have taken note of the other terms that mean the same as EMF or potential difference. Don't confuse the two. resistance. We must know this parameter. This is the property of a material to oppose or to resist the movement of electrons or the movement of charge carriers. That's a resistance. A material that offers that opposition or resistance is called a resistor. And we know that conductors have got very low resistance, while insulators or non-conductors have got very high resistance. Take note that the resistance is measured in ohms, as we saw, and the symbol for ohm is the Greek letter omega. The letter R represents resistance and not resistor. What is a resistor? This is a two-terminal passive component that limits the flow of current. You remember current limiting resistor. Then resistance is the measure of the material's opposition to the flow of current, and as stated, its unit is ohm. We now want to define what is an ohm. It is the amount of resistance which allows 1 ampere of current to flow when the applied voltage is 1 volt. I like that definition. So 1 volt divided by 1 ampere gives us 1 ohm. What is the importance of resistance? Without resistance, every electric circuit would be a short circuit, and we will hear kaputi, kaputi, kaputi everywhere when you power up devices. So short circuit is not needed, guys, because it results in a flow of high current, which can be dangerous to us human beings. More on resistance and resistivity. We now want to state a mathematical expression to show the relationship between the resistance, length of wire, cross-sectional area, the material. And we are saying we are now going to have the constant of proportionality, and that constant of proportionality is what we call the resistivity of the material, and its symbol is rho, which is a Greek letter. Hence, we can safely say resistance of a material is equal to rho L over A, where L is the length of the conductor, A is the cross-sectional area, and rho is the resistivity in ohm meters. How do you define resistivity? You might be asked to define resistivity. This is the resistance that exists between opposite faces of a 1 meter cube of a material measured at a specific temperature or defined temperature. That's the definition for resistivity, which is our constant of proportionality in our equation. I hope, guys, you are enjoying, and if you are enjoying, don't forget the subscribe button. Worked problem. We've got a question there. Guys, I think get hold of your calculator. If you don't get this, then you need a video on how to use your scientific calculator, and I will do that. Calculate the resistance of a 100-meter length of wire. This is the length having a cross-sectional area of 0.2 square millimeters and having a resistivity of 40 micro ohm centimeter. This must be converted to meters. Length is in meters, is fine, and this also must be converted to square meters, and I've done that in my equation. Guys, first write your formula. Resistance is equal to rho L over A. Then you put the values. 40, it's a micro there. This is 40 micro. Then you change that to meters. Then you multiply by your length. Then you divide by the cross-sectional area. And I've converted that to square meters. Then you must get 2000 ohms, which is equal to 2 kilo ohm. If you find any challenges in changing the units from one unit to another, guys, you have got my email. You can do that on YouTube under comments. I'll be more than willing to respond to you there and then. So guys, you must be able to solve calculations. If you are asked to find A, which means with your cross-sectional area, which means you have to make A the subject of your formula. Hence, it becomes cross-sectional area is equal to rho L over R. If you are asked to find rho, that's the same. You make rho the subject of your formula. So rho is equal to resistance times cross-sectional area divided by length, and you can do that for any parameter in the equation. Temperature coefficient of resistance. You must be able to calculate this at the end of this presentation. Guys, we know that the resistance of a conductor increases with temperature, while the resistance of semiconductors and insulators decreases with increase in temperature of the material. We have got this parameter called temperature coefficient of resistance, and it can be defined as increase in the resistance of a 1 ohm resistor of a material when it is subjected to an increase in temperature of 1 degrees Celsius. Its symbol is the Greek letter alpha. Then the resistance due to a higher temperature, how do you find it? It is equal to the original resistance of a particular material multiplied by the temperature coefficient, which we have defined as alpha, and also multiplied by the rise in temperature in degrees Celsius. That is, mathematically, resistance increase is equal to the original resistance R multiplied by alpha, the temperature coefficient of resistance, and multiplied by the degree rise in temperature. Take note that we are only finding the resistance increase. Then after finding the resistance increase, that value is added to the original resistance of a material so that we can find the resistance at a new temperature. So we are finding we are trying to deduce that when a temperature is increased, say from 0 degrees Celsius to 1 degrees Celsius, the resistance of that particular material changes. So to find the new resistance, you add the result from you add the resistance increase to the original resistance. Let's see. It is going to become clear if we proceed to the next slide. Let's see. We've got the following statements. Some copper wire of resistance 1 ohm is heated through to 1 degree Celsius and its resistance is then measured as, that's the new resistance, 1.004312. Then how do you find alpha? It means that alpha multiplied by 1 ohm multiplied by 1 degree Celsius give us the resistance, which is the rise in resistance. So it means that if you make alpha the subject of the formula, it will be equal to 0.0043 ohm per degree Celsius for copper. And how can you deduce that? This is because 1 ohm is the original resistance, meaning that the resistance increase is equal to R times the temperature coefficient of resistance alpha times the degree rise, which is equal to 1 as stated. That is 1 times 0.0043 times 1. And please take note of the following important parameters. The original increase at 0 degree Celsius is equal to R naught. So R naught stands for resistance at 0 degrees Celsius. Then R theta is the new resistance after a temperature degree rise of theta degrees Celsius. Guys, you must take note of those parameters. Then our alpha is the temperature coefficient of resistance. Don't worry. Then the units used are usually expressed as per degree Celsius. So our alpha can be expressed as 0.0043 per degree Celsius, which means that 0 degree Celsius, we know what it is. It is the degree rise in temperature. We now have another scenario which we are given so that we can understand more. If 1 ohm resistor of copper is heated through 100 degrees Celsius, then the resistance at 100 degrees Celsius is going to be 1 plus, then you add the rise in temperature 100 degrees Celsius times the temperature coefficient of resistance, which is 0.0043. We find the new resistance of the copper material and it is 1.43 ohm. Let's go to the next slide where we are going to solve some problems. Guys, you must know that a formula must be at your fingertips. We are given the following statement. If the resistance of a material is at 0 degrees is known, then its resistance at any other temperature can be determined from the following formula. It's R theta, which is the resistance at a new temperature, is equal to its resistance at 0 degrees Celsius in brackets 1 plus the attenuation coefficient at 0 degrees Celsius times the new temperature, which is equal to theta. If we make the resistance at 0 degrees Celsius the subject of the formula, it means we are dividing both sides by 1 plus attenuation coefficient at 0 degrees Celsius times the new temperature. So it becomes R theta divided by 1 plus A naught theta. And our parameters are R naught is equal to resistance at 0 degrees Celsius. R theta is the resistance at the new temperature, and our A naught is equal to the temperature coefficient of resistance at 0 degrees Celsius. Guys, take note of those two formulas. They are very, very important for you. Temperature coefficient of resistance, guys, I think we saw that change in resistance is 1. We saw that it is directly proportional to the initial resistance and it is also directly proportional to the change in temperature. We know that if temperature changes, resistance is also affected. And we know that it depends on the nature of the material. Is it a conductor? Is it an alloy? Is it an insulator? Is it a semiconductor? But normally when we are talking about semiconductors, we'll be talking about electronics. So it is simple. That slide is simply stating the factors that affect change in resistance. a past exam question for you to practice. A coil of copper wire has a resistance of 100 ohms when its temperature is 0 degrees Celsius. We are being asked to determine its resistance at 70 degrees Celsius if the temperature coefficient at 0 degrees Celsius is 0.0043 per degree Celsius. Solution. Guys, we must know this formula. R theta is the new resistance at 70 degrees Celsius, and how is it found? This is equal to resistance at 0 degrees Celsius in brackets 1 plus its attenuation coefficient, its temperature coefficient of resistance at 0 degrees Celsius multiplied by the temperature rise, which is theta. So our theta is our new resistance, our new temperature, and this is 70 degrees Celsius. So R at 70 degrees Celsius is equal to the resistance at 0 degrees Celsius 100 in brackets 1 plus attenuation, the temperature coefficient of resistance 0.0043 multiplied by the degree rise in temperature, which is 70. If you multiply this, get 0.301. If you add this to 1, you get this. Then you multiply it by the temperature. You must get a higher value, which is close to 130.1 ohms. So you can see that if you increase the temperature of copper, which is our conductor in this case, its resistance is going to change. It is also going to increase. So guys, take note of this formula. You must know it by heart. It must be at your fingertips, or else you find the going tough. Work the problem number 2. This time you are being asked to find resistance at 0 degrees Celsius after being given a resistance of 27 ohms at a temperature of 35 degrees Celsius. We want to see whether the resistance will be lower than 27 ohms. Let's see. This time, guys, you must make your R not the subject of the formula. And how is it determined? We saw that from a slide before. Your resistance at 0 degrees Celsius is your resistance at, in this case, 35 degrees Celsius divided by 1 plus the attenuation coefficient and also the rise in temperature. And if you solve this, guys, you must get 23.83 ohms. Practice, guys. Practice. Get your calculator, put the values. If you don't get this value, it means you have got some challenges, and that is the reason why I'm there to help you in your time of need. So the resistance at 0 degrees Celsius must be lower than at 35 degrees Celsius. As you can see, it is 23.83 before going through a temperature rise of 35 degrees Celsius from 0 degrees Celsius. This one is for you. If you don't get 960 ohms, then there's something wrong with your calculation. You are given a carbon resistor with a resistance of 1 kilo ohm at 0 degrees Celsius. Want to find its new resistance at 80 degrees Celsius, and the assumption is that the temperature coefficient of resistance at 0 degrees Celsius is equal to 0.005 per degree Celsius. Your answer must be 960 ohms. Guys, this is easy. If you solve and you get that, don't forget to send me the screenshot to or on YouTube or on my WhatsApp number, or even my email. Guys, we've come to the last slide of fundamentals of electricity, and we are going to look at conductance. The symbol is capital letter G. What is conductance? Conductance is the ease with which electrons or current can be allowed to pass through a material. Its unit is measured in Siemens, and the unit symbol is capital letter S. The unit used to be mho a few years back, which is the word ohm spelled backwards, and the unit symbol then was inverted omega, which is a unit for which is a unit symbol for resistance. How do you find a conductance capital letter G? This is equals to 1 over R, and guys, we have covered R is equals to rho L over L. So if you find its inverse, it's A over rho L. That's the formula for calculating in inductance. Don't say I didn't tell you. This is our last slide, guys, and I know it is so taxing, but it is worth it. Practice all the examples, know your calculator, and if you are benefiting from the course, guys, your favorite channel, don't forget to hit the subscribe button. Until we meet, guys, bye for now. In our next video, we'll be looking at direct current circuits, and I hope you are going to enjoy.